When we write down an equation with multiple variables, that equation can define either an explicit or implicit relationship. For example, xy equals 1 is an example of an implicit relationship. If we fix a value for either x or y, we can solve for the other variable. As an example, setting x equals 2 allows us to solve the corresponding equation to find that y is equal to 1/2. On the other hand, the equation y equals 1 over x is an explicit relationship. It tells me exactly how one variable is related to the other. In this case, if x equals 2, there's no solving that needs to be done. We just compute the right-hand side to find that y is equal to 1/2. In either case, we get that xy equals 2 1/2 satisfies these two equations. And in fact, any point which satisfies the top equation also satisfies the bottom equation. Now, however, not all equations give rise to functional relationships. That is, not every implicit relationship has a corresponding explicit relationship. A classic example is that of the circle, whose equation is given by x squared plus y squared equals 1. If we're given the point x equals 1/2 and we plug that into this equation, we can solve for y. However, this one value of x produces two y values, which says that y cannot be a function of x. This is clear from the graph, which fails the vertical line test when x is equal to 1/2. So with that review of implicit and explicit relationships, let's turn to our goal, which is to discuss derivatives in this context. Note that if we're willing to ignore some points, we can find a functional relationship. In the case of the circle, we might ignore the entire lower half, which would then allow us to write y as a function of x. Doing this, can we find the derivative of y with respect to x without having to actually solve for that explicit relationship? And two, can we find a general expression for the derivative, which works for any pair of points which satisfies our given equation? We'll be able to do both of these things, but the procedure is a bit tricky. I'll try to spell it out slowly so you get an idea of how it works. The first thing that we do is we pretend that we can write y as a function of x, and we're going to take this and we're going to plug this into our equation. In this case, we don't know what f is, but we don't actually care. In the case of the circle, replacing y with f of x gives us this. Next up, we differentiate with respect to x. Now we're almost certainly going to have to use the chain rule wherever an f of x occurs. In the case of the circle, the x squared differentiates to just give us 2x, while the f of x squared term differentiates to give 2f of x f prime of x. The right-hand side, being a constant, just differentiates to 0. Having done this, we're looking for f prime of x, so let's solve for it. Rearranging everything and doing the appropriate cancellations is going to give us negative x divided by f of x. And note that a consequence of this procedure is that our derivative will generally depend upon f itself. That's a little weird, but it's not going to end up being a problem. Now notationally, rather than lug that f of x term around, we often just remember that y is supposed to be a function of x. Our equation of the circle therefore doesn't change, but when we differentiate, we treat y as though it depends upon x. The result is that we have to apply the chain rule to the y squared term, giving 2y dy dx. This term is the exact same thing as the 2f of x f prime of x when y is equal to f of x. Thus, solving for dy dx, we get negative x over y, which is again the same thing as negative x over f of x. If we know a set of points, we can then actually find a numerical value for dy dx. For example, we found that 1/2 root 3 over 2 lies on the circle, so we can plug that into our expression for dy dx to get the following. But we know there's another set of points that occur when x is equal to 1/2, but that time, y is equal to negative root 3 over 2. The math is similar, but we end up getting a different sign of the derivative out. If you look at the graph of the circle and think about the tangent lines when x is equal to half, you'll see that this is consistent with what we found here. Note that there's nothing special about treating y as a function of x. We could have treated x as a function of y and found dx dy instead. I recommend you give it a shot and see if you can work that out for yourself. For an example that isn't the circle, let's turn our attention to the following equation, which defines a relationship between x and y. Let's find dy dx when y is equal to 0. We must first find the value of x when y is equal to 0. So we'll plug y equals 0 into our equation to get the following. This simplifies pretty quickly to give us x equals 1. So x comma y equals 1 comma 0 is our point of interest. Now let's differentiate. This would be a great time to stop the video and see if you can do this on your own and check if you get the right answer. To differentiate the first term, we'll have to use both the product and chain rules. Remember that y is a function of x. The second term also requires a product rule. At this point, you could solve for dy dx, but it would be messy, and there's a good chance that you would make a mistake. So instead, let's just plug x equals 1 and y equals 0 into this equation. Doing the substitution at this point is going to dramatically simplify the equation. And what's left over is just 1 plus 2 times dy dx equals 0. So dy dx is negative a half. I'd really recommend that you try redoing this problem, but solve for dx dy. Can you guess a relationship between dy dx and dx dy?